My name is Alejandro, and I will be talking to you about JavaScript engines. And since in all the resources and documentation, JavaScript engines are referenced as virtual machines, it could also be considered as an introduction to a subtype of virtual machines. But before we continue, I wanted to give you some background on the motivation for this talk. So it's story time. I write JavaScript for a living, and earlier this year, I came across a JS perf for doing a string to number conversion. And it had different ways to do the conversion, the plus operator, the number constructor, bitwise operators, and so on. And I remember seeing the charts of the results, and one of the tests on Firefox was off the charts. It was 50 times faster than any of the other competitors. And so I tweeted, cool, they are doing some voodoo magic at Mozilla. And shortly after, these Google engineers, Lava, replied, don't trust that. I'm guessing it's being dead code eliminated. He worked at the BA team, and he's also super smart. So even I had no idea what he meant. At that point, I understood that I work every day with these pieces of software, but I didn't know how they work and how they optimize code. So I started my path going through the history of JavaScript engines. This is me. If you can't recognize me, probably it's the hair. I look at the history for JavaScript engines, and I found an inflection point around 2006, 2007. Before that time, JavaScript engines were pretty straightforward. So they would grab the source code, and they would parse it to an abstract syntax tree, or AST for short. The AST will omit comments, tabs, spaces, parentheses, curly braces, all things that are part of the syntax and will represent expressions and blocks as nodes in a tree structure. So the engine would grab the AST and would transform that into bytecode. Bytecode can be described as a well-defined set of instructions, and it's also considered as a portable representation, since it wouldn't change through different CPU architectures. On the other hand, machine code is architecture specific, meaning that for the same lines of JavaScript, its machine code will vary from mobile CPUs to desktop or laptop CPUs. So after that, the final step needed would be to execute the program, and it's also often described as a really big switch statement, that for each bytecode instruction in the bytecode, it will execute that and will jump to the appropriate code. The final step after that, like in most high-level languages, JavaScript will not deal with object allocations explicitly. So you can create objects, and those objects will live in the heap section of the program, and the engine would allocate them internally. So in order to reuse those precious bits of memory, the system will need a garbage collection system. And I know Sophia talked about this, and she really did a good job. So we'll leave those details for later, and we will pass to the architecture part. Turns out this pretty straightforward setup was kind of slow, where slow means implicitly comparing to the performance of a C or C++ program after all the optimizations are applied. A group of brilliant people worked on improving this architecture in the 70s for Fortran and in the 80s for Smalltalk and Self runtimes. So they came up with an idea of adaptive optimization. And the idea is identify the pieces of your program that are executed often, or mostly functions, also called as hot functions, and optimize them during execution time. Hence, the names for just-in-time compiler or JIT compiler for short. So this is what it would look like a JavaScript engine at that moment. So we have our JIT compiler, and the basis for most engines that we will discuss here are an interpreter that would receive the source code and two compilers. One that would execute, will optimize compilation time, and another one that would optimize execution time. So switching to a real-world architecture, SpiderMonkey is not too far from the previous example. It had an interpreter that will receive the source code, will transform that into bytecode, and will initially execute it without compilation. After the number of times a function is executed goes over a certain threshold, it will then optimize it with the baseline JIT. After the number of times a function goes over a second threshold, it will then be categorized as potentially to be optimized with a really, really good optimization. And that's when IOMonkey kicks in. So IOMonkey will grab the bytecode plus the type information that the system collected and will recompile the function. All the compiled code under optimistic assumptions can be invalidated with a new behavior on the program. But unlike the previous example, all the code would bail out to the baseline sheet instead of the interpreter. So that would be somewhat best performant than the other one. ChakraCore shares a similar architecture to SpiderMonkey. It has an interpreter, a non-optimizing compiler, also called as simple sheet, and an optimizing compiler called full sheet. The interesting part is that it can fire additional threads to compile or to run the garbage collector. As Nolan said yesterday, once garbage collection is running, your script will not be running. So if you can fire an additional thread, it will then be possible to run the garbage collection system while the script is running. Say you're running the engine in a 4-core CPU, in theory you could take advantage and parallelize compilation or garbage collector in 3 cores. Let's switch to the case of V8. They have recently switched to 4-tiered architecture, an interpreter, a non-optimizing compiler, and 2 optimizing compilers, Crankshaft and Turbofan. The interpreter was recently added to the engine, and its goal is to trade execution time to reduce the memory consumption in return. Previous to the addition of the interpreter, the code was parsed and transformed to a syntax tree, and all the compilers will receive the syntax tree as input. The full cogent compiler resembles to the SpiderMonkey baseline compiler. Both will create inline caches. If V8's profiler identifies that a function is taking a good proportion of the execution time, then it will notify the engine that it needs optimization. Both Crankshaft and Turbofan optimizes code with type information, Turbofan being the newest compiler, and also the one that complements Crankshaft to optimize features like ES6. JavaScript core has also a 4-tiered architecture, an interpreter, a non-optimizing compiler, and two optimizing compilers, DFG and FTL. In all of their compilers, JavaScript core is taking advantage of inline caches as well. If a statement executes more than 100 times, or the function is executed more than 6 times, then it will be compiled using the baseline compiler. If that number goes over 1,000 times for the statement, or the function is executed over 66 times, then it will be targeted by the DFG compiler. Once that number reaches 10,000, it will then apply for optimization with the FTL compiler. And as you can see, one of their components is LLVM, which is a compiler that applies all sort of optimizations, and it's also a different project outside JavaScript core, and serves as backend for FTL. That means the engine would gather type information, the bytecode, and transform that into a lower level representation to feed into LLVM, and that would output machine code. They have recently changed a new backend for the FTL called V3 in order to keep all the optimizations they wanted, but to reduce compilation time. So now that we discussed all the major architectures, let's talk about what optimizations are they are applying, some of them. Let's say you have a loop executing many times, and it's inside its body a single expression, adding the variable were incremented, multiplied by some arbitrary number. Very reasonable performance improvement would be to make the calculation once and reference it by a temporary variable. All the engines mentioned here are applying that optimization internally, and it's called loop invariant code motion. Here you can see how the code would be after applying the optimization. One of the simplest optimizations that JIT compiler could apply is called function inlining. Let's come back to the canonical loop. And inside its body, we decide to execute a function. If the loop iterates a certain amount of times, the profiler will identify the function as hot. And if some condition is applied, it will grab the function's body, copy it, and paste it directly inside the loop. Now, you may be wondering why it should be faster since it's the same code. In low-level programming languages, calling a function would end up in a context switch. For example, just after calling the function will have to save all the current status or push all the registers to the stack, and before returning, it would have to resume the previous context, popping the saved registers from the stack. Let's go to a different optimization. Let's say you have the canonical loop and you decide to execute some expression. It could be any expression do you want. Here we have a simple sum. It could be optimized, but just avoiding doing anything at all if you don't have side effects. For example, assigning a variable or returning inside the loop. This optimization is called dead code elimination. And even some compilers would even go further and delete the whole loop, like the JVM, for example. Be aware that some features of JavaScript will inhibit type-specializing optimizations, like the eval function, the with operator, and the try-catch block. Now we have talked about a few of the optimizations that these engines applied. Let's go over the garbage collection systems. Generational garbage collectors will group objects by their lifetime and will assume that young objects are more likely to die than all objects. This kind of a strategy will create new objects in a nursery space and promote long-lived objects to a tenor space. Incremental garbage collectors interleave their work with the main program, producing shorter pauses. On the contrary, a stop-the-world approach would halt the execution of the program until a full collection is done. Garbage collectors can also be categorized as precise or conservative. Precise garbage collectors can identify all the references, and conservative ones look at memory patterns to find references in the heap. The last approach could potentially lead to false positives, but that's not always a problem in practice. By seeing these similarities and differences, I was able to learn so much about these engines. But for me, the most important part is that they are all open source. And that means that they don't fear to show their code, but instead they are willing to learn from each other, a privilege rarely seen in this industry. In this link, you can find all the resources that I used while working on this presentation. If you want to read about JIT compilers or garbage collectors and you're interested in the details, there's a lot of material there. While working on this presentation, I came across with a lot of questions, and my perspective changed from some of them. One question that I had was, well, how do you measure performance in all of these engines? And even if the answer to that is complicated, I'm sure micro benchmarks would not be a good measure. I know there's extensive benchmarks for each browser vendor out there, but I think your applications will definitely be the decisive one. It will depend on what types of allocations you're doing, what types, which are your hot functions, and many, many other cases. That being said, I think we all should strive for maintainable and clean code. All the optimizations techniques that I came across were more related to dynamic typing or functions being monomorphic and had nothing to do with using obscure bitwise operators for doing a string to number conversion. Thank you.
All right.